Okay, so in this one, I want to show you or demonstrate how matrices can be used to help us solve linear systems. Now, this is the type of problem that you probably learned how to do at some point earlier in your math career. But what we're going to do is re-represent the problem using matrices. Okay, so yeah, solving linear systems. So let's just do this via example. I think that's maybe the easiest way of doing this. Let's take the following example, which actually I'm just ripping from the textbook just for convenience. Let's take the linear system 2x1 plus 2x2 plus 2x3 equals 2. Okay, that's a linear equation in x1, x2, and x3. Let's take this equation, x1 plus x2 plus 3x3 equals 5. There's another linear equation. And let's put one more. x1 plus 4x2 plus x3 equals 10. So you probably learned at some point how to solve these kinds of things. What we're trying to hunt for, what we're hunting for in trying to solve this is to find numbers x1, x2, and x3 which solve all three of these equations simultaneously. Now there's a technique for re-representing this as a matrix equation. Let me show you that. So we can rewrite this thing here. Actually, I'm going to move it over a little bit. I'm going to move it just to here. And then maybe erase this. Okay, whatever. We can re-represent this thing using a matrix or a matrix equation. Here, I'm going to do it now. I'm going to have a matrix 2, 2, 2, 1, 1, 3, and 1, 4, 1. Okay? That's a 3 by 3 matrix. And you see, I hope, where I got these numbers from. These are the coefficients of x1, x2, and x3 in each of these three equations. Each equation gets one row, and the coefficients are organized in order. Okay? Now, I can multiply this matrix by a 3 by 1 column vector whose entries are x1, x2, and x3. Now, think. Notice, if you do this matrix multiplication, what you're going to do is take 2, 2, 2 and multiply it by x1, x2, x3. Take the dot product, right? But that's exactly this expression here. Do you agree? Similarly, when you take 1, 1, 3 and you take the dot product with this vector, you get exactly this expression here. And similarly, this setup, right? So you understand why this matrix product in red here, this one right here, gives you the right-hand sides, the left-hand sides of this system of equations. To make this this matrix equation, to finish it out, what we're going to do is set this thing equal to the 3 by 1 matrix 2, 5, 10. And this is a matrix equation, which if we can find the solution to x1, x2, x3, we win, because we'll have found the values which make this matrix equation true, which are exactly the values of x1, x2, and x3, which make that system be solved. Hopefully that's clear. Okay, now, rather than attacking this equation, which is sometimes written in notation a times x equals b, okay, and these little hats mean that we're talking about vectors with x and b, column vectors. Rather than doing that, sometimes what we do is we construct what's called the augmented matrix for this system. And this is, don't be, I know it's a scary word. All it means is we're going to take this matrix A and tack on B as another column. So this matrix in particular is going to be given by 2, 2, 2, 2, 1, 1, 3, 5, and then 1, 4, 1, 10. Okay, that's what's called the augmented matrix. Sometimes people will do little things like this, but I'm not too worried about that. All right? Okay. Now, we are going to manipulate this matrix using these three operations, which are called elementary row operations. And there are three types of elementary row operations that we will allow into our life. The first is to add a multiple of one row to another. It can be a negative multiple of one row to another. So that's kind of like subtracting. In any case, you're also allowed to swap any two rows. And the last move that we can do is multiply a row by a non-zero number. These three elementary row operations are what you can use to manipulate your matrix. And yeah, they're going to change your matrix, but the point about these elementary row operations is that applying these EROs do not change the solution. To the linear system. Okay? So we're allowed to apply these in any order that we want, as many times as we want, and we will never change in the process of applying these the values of x1, x2, and x3, the values here, which solve the linear system. Okay, we preserve the system. So these are like moves that we're allowed to do, okay, to our matrix without affecting our solution. And hopefully we can use them to solve our system. How? Okay, let me demonstrate with an example. So here is me applying elementary row operations, EROs, to solve the above system. I'm going to start with the augmented matrix I've got here. I'm going to make a duplicate. I'm going to move it down here. Okay, there's my, that's my starting point, is the augmented matrix. Now I'm going to use elementary row operations to transform this matrix and get it into a state where I can easily read off the solution to the linear system. So how? Well, the first move that I'll do is I'm going to multiply row 1 by 1/2. So maybe I'll write that. Multiply row 1, can you deal, by 1/2. And if I do that, that's going to result in this following matrix: 1, 1, 1, 1, 1, 1, 3, 5, and 1, 4, 1, 10. Notice that the other two rows do not change under this. It's only row 1 which has changed. And the effect has been to multiply each entry by 1/2. Okay. Okay. Next, what I'm going to do is I'm going to add -1 times row 1 to row 2. I know this is the right thing to do from experience, and you're going to see why, hopefully. If I do that, the first row does not change, because what's going to get affected here is row 2. Row 2 becomes 0, 0, 1, -1, 2, and then 4. Do you follow? Then I have 1, 4, 1, 10. The next thing I'm going to do is attempt to clear. So I've cleared out this entry. By that I mean I've made it 0. I'm going to attempt to clear out now this entry. So how can I do that? I can again add -1 row 1 to row 2. Maybe I'll do that down here. Add -1 row 1, sorry, to row 3. Did I say that wrong? I'll write it right. To row 3. And what do I get when I do this? Oh, this is going to be interesting. 1, 1, 1, 1, 0, 0, 2, 4, And then I have 0, 3, 0, 9. Hopefully I did that right. Okay. Great, great, great. Next move I'm going to do is I'm going to swap row 2 and row 3. This is another, and row 3. This is another elementary row operation, and the effect of it is the following: 1, 1, 1, 1, 0, 3, 0, 9, 0, 0, 2, 4. Okay? Next, what I'm going to do, because I'm satisfied with this column right now, okay, is I'm going to use this non-zero entry here. This is sometimes called a pivot, okay? I'm going to make that pivot equal to 1 by multiplying row 2 by 1/3. Multiply row 2 by 1/3. I'm allowed because 1/3 is not 0. We got 1, 1, 1, 1, 0, 1, 0, 3, 0, 0, 2, 4. Okay, pretty happy. Next thing, I'm going to kill this 1. How? By adding -1 row 2 to row 1. Do you see that I can kill this 1 here by doing that? Add negative row 2 to row 1. If I do this correctly, notice this 1 here doesn't change. That's nice. 0, 1, -3. So I think that's -2 there. 0, 1, 0, 3. Nothing else changes. All right. Next, I'm going to endeavor to make this column look kind of like these other two columns. I see 1, 0, 0. That's nice. I see 0, 1, 0. I'm happy. I want to make this last column look like 0, 0, 1. Because if I do that, okay, this becomes... I can do that by first multiplying row 3 by 1/2. And what I get is 1, 0, 1, -2, 0, 1, 0, 3, and 0, 0, 0, 1, 2. And finally, I can now kill this 1 here by adding negative row 3 to row 1. And what I get is 1, 0, 0, -4, 0, 1, 0, 3, 0, 0, 1, 2. Okay. All right. That was a lot there, right? This was a long process, quite tedious. Get used to it, okay? This is elementary row operations. By the way, no, never mind. I'm not going to say it out loud. Okay. Very smart of me to not do that, because it would just be discouraging to you all. All right. So here we've got all this. Now, what is the result of all of this? The idea is that we can now convert what we have here at the very end back into a linear system. Because remember this. So if we convert it back into a linear system, so think of it this way. To start with, we started with this linear system here, and we converted it into this augmented matrix, right? We tracked the coefficients in the first 3 columns, and we tracked the sort of right-hand side of the right-hand side of the linear system with this last column. Okay, so I'm going to do the same thing. I'm going to track the coefficients with the first 3 columns and track what the right-hand side is with the last column. And if I do that, what I get is that x1 plus 0x2 plus 0x3, so just x1, is equal to -4. That's the first equation from the first row. The second row is telling me x2 is equal to +3. And the last row is telling me x3 is equal to 2. And indeed, what this is the solution It turns out there's a unique solution to this linear system. Do you believe it? You don't need to believe it. You can just check it yourself. You can check that when you replace x1 by -4, x2 by 3, and x3 by 2, which I believe were the answers. Yeah, -4, 3, and 2. That indeed you get 0. Okay? Another way of doing that, of course, would be to plug x1, x2, x3 being -4, 3, 2 here, and then do this matrix multiplication and see that you get 2, 5, 10. Okay? This process is called row reduction. This process is called row reduction. And it is very commonly used, and we will use it, to find solutions to linear systems. And you might be asking yourself, and it's a legit question, well, why are we learning this in differential equations? There's no derivatives involved here. There's no differential equations. Well, because we're going to use these techniques for solving linear systems in the service of solving linear systems of differential equations, okay, as we will see. Now, let me give you another alternative here. Example. Let's say that we had something like 2, 1, 3, 5. Oh, sorry. I should use the system notation for now. So if we had 2x plus y equals -1 and 4x minus y, okay, fine, equals 6. I don't know what I'm doing. Here's a linear system, and I know you could have solved this in, a long time ago, but I just want to demonstrate something. Let's convert this to a matrix equation. Now, not an augmented matrix, but rather a matrix equation. So if I do that, this becomes 2, 1, 4, -1 times xy is equal to -1, 6. Yes? Now, let's call this matrix here A. This matrix is A. What's A inverse? Well, you should know, and this is maybe something that's useful to remember, A inverse, so for a 2 by 2 matrix, maybe I'll do this in red over here. So if A is equal to the 2 by 2 matrix A, B, C, D, and the determinant is non-zero, because remember, the determinant being non-zero means that A inverse exists. Then A inverse can be written as 1 over AD minus BC times, and it's a weird amalgam. It's like D, A, and then negative signs on the off diagonals like this. They don't change positions, but they get negative signs. Okay? And you can check this yourself. This is the truth. This is all good. But the point that I'm trying to make here is that we can use this fact about 2 by 2 matrices to write down A inverse in our problem. So what's the determinant, first of all? It's going to be 1. So I'm just following this definition here, not the determinant. So 1 over the determinant. The determinant is -2 minus 4, which is -6. So I don't know why I wrote that so weird. It's 1 over -6, or -1/6. So that's going to be the number out front, times, so we're going to swap the diagonal elements. So -1 and then 2 here. And then we're going to put negative signs in front of the off diagonal elements. That's A inverse. Okay? Why is this cool? Because if I think of this equation here as being AX equals B, then what I can do is multiply both sides of this equation by A inverse. So I multiply both sides by A inverse, like this. And what's A inverse times A? It's the identity matrix. And the identity matrix times anything is just that thing. So in other words, what we end up with is X equals A inverse B. Because again, this part right here is simply the identity matrix. What that means is that we have a solution for X. It's simply A inverse B. What's playing the role of B here in this problem? Negative 1, 6. Okay? And so we can solve our problem. Our problem becomes, the solution to our problem rather, becomes x, y is equal to A inverse, which is negative 1/6 times negative 1, negative 1, 4, 2, multiplied by negative 1, 6. Oh, it looks so weird because it turns out that the B I chose was exactly, looked like 1 over the determinant, but I hope you're following. Yeah. This ends up being negative 1/6, and now I just do matrix multiplication. So negative 1 times negative 1 is 1 minus 6. I think that's negative 5. And then negative 4 plus 12. Negative 4 plus 12 is 8. So I think I get, for my answer, 5/6 and 8/6, which is 4/3. That's my X and that's my Y. You can check it by plugging these numbers in or solving the system yourself. And I hope that you'll get the same thing, assuming I did everything right. Does this seem plausible? 10/6 plus... wait, something's wrong. Oh, am I missing a negative sign? I'm missing a negative sign here. Thank you. 10/6 minus 8/6. Wait, something is wrong here. What have I done? Did I do something wrong? 4 plus 12. 5/6 is 10/6, which is 5/3 minus 4/3. Did I compute the determinant wrong? Negative 2 minus 4. Negative 6. Shit. I really blew it. Wait. Maybe it's good for you and healthy for you to see this. Negative 5/6, negative 5/3, or 5/3 minus 4/3 is 1/3. Why am I getting... What have I done wrong? Negative 1 times negative 1 is 1. Negative 6 is negative 5. Negative... What did I do wrong? Oh my God. I just found the issue. I missed a negative sign. It's right here. Okay, so it's actually -5. That looks right. But it should be 4 plus 12. This should be 4 plus 12, which is 16. So it should be 5/6 and then -8/3 or 16/6. Whatever. So does this work? Yes, this works now. Okay. Maybe this is a good learning experience because what did I just do? I checked my answer and it didn't feel right. Okay, and rather than just um, giving up, I broke my brain to detect that I missed this negative sign right here. Okay, I mean I wrote it down, I just didn't copy it right, which is exactly the kind of thing I see on your exams and such. But I did find it eventually, and everything is restored now. I think it's fine to leave this in. If you stopped watching 5 minutes ago when I went dead silent because I couldn't figure out what was going wrong, um, well, you're not seeing this now, but if you did stick around, I appreciate you. And I'm going to end the video here. Okay? Bye.